takes each of these principal variables and relates them. I don't know why I put a delta there, sorry. Now, there's a couple of things I'll throw in here just so we know. This could be any velocity, initial, final, or something in the middle. It just says if you want the instantaneous linear velocity and you know how fast something is spinning, you could figure out its linear velocity. Now, this side here has two different meanings. And that's what I think is hard. So let's see if we can be clear about the two different meanings here. This side needs something that's spinning. So I think that's easy. Something has to be spinning for this side. But the left side can mean how far or fast something moves. I'm going to put travels instead. So how far or how fast something travels. This pertains to things that are rolling. So if you have an object rolling, how fast it changes location depends on how fast it spins. Does that make sense? I mean, I think it's obvious, but it also means tangential. So this is for something that's not rolling, something that's staying in place. So it doesn't matter which one we're talking about. So I don't want to put a T next to each one of those to indicate tangential, but tangential means tangent to the path it's traveling on. So we need to understand it could be both of them. We're going to do examples of each. You guys ready? So tuck that away. You need this, be able to produce it. And you're probably going to want your slew of 5 motion equations in front of you too, which is why I kind of put that thing together that had all of them, both all the angular and all the linear. Yeah.
Are you saying the first two equations are for things that are rolling? The last one's for things
No. Everything over here can apply to things that are rolling or things that are spinning. It can be either one. So let's take a look at 2 different examples, that one of each. One for something that's rolling, and then one for something that's spinning, so you get the idea of what I'm talking about, okay? Let's start with something that okay with you guys? So, spinning. So I'm going to choose something simple, something that you guys have probably done before. So you ever been on one of those rides where, I'm not going to draw the whole ride, just a part of it, but they're at the carnival. So you're like on something over here, but the whole thing is spinning in a circle. You guys ever ridden anything like that? There's a bunch of these kinds of things at the carnival. They do it all sorts of different ways. So the kiddie rides might have like a little motorcycle strapped here, and a little kid rides on what looks like a motorcycle, but it's just on an arm and it goes in a circle. Little kids do that. Sometimes it lifts them into the air and stuff like that. Does that make sense? If you're a bigger kid, you might be lucky enough to have it have, say, another arm that is also spinning. So you sit over here, this spins and this spins. They're called like the zipper or stuff like that. You guys know what I'm talking about now? I don't want to make it that complicated, so let's just talk about the kiddie ride, the one that has like the little car at the end of a bar and it goes in a circle. And there's like 8 of those, right? And a bunch of kids are all on it. Is that okay? All right, so that's what we're going to talk about. So let's go back, make it simple. So there, and you're at the end of this bar, or maybe your little brother is, and your responsibility was to ride with them because your little brother was scared or some crap like that. That happens. Well, anybody have little siblings? Anybody is a little sibling? No. There was probably a time where your older sibling had to do something with you that they didn't want to do, but you wanted to do, and your parents said, go with your little brother, go with your little sister. That happened, right? And have you been the older one where that's been told to you? Yes, we parents love that. It's built-in babysitting. You go ride that stupid ride with them because I don't want to ride it with them. And take the kid. That's why you have a second kid. Here, I was worried you wouldn't make any friends. I created a friend for you. Go play. So, if you don't believe that's true, then talk to your parents. It's definitely true. So, let's say that the kid gets on the ride, and if it's a small children's ride, this is probably no more than 2 meters. They keep them pretty small. And let's say it starts from rest and gets up to a speed where it's going around once every 3 seconds. Okay? 1, 1,000, 2, 1,000, 3, 1,000. That seems like a reasonable ride for a little kid. All good? All right, so let's consider that it takes maybe 10 seconds to get up to speed. All right, everybody have all the pieces I just said. So I'm got delta theta, we got omega naught, omega, alpha, and t. But we also have delta x, v naught, v, a, and t. Okay, we have both sets of variables here because we don't know what the problem is going to ask. So it could ask any number of things, but some things were given to us. So let's consider the things that were given to us. They said that it started from rest, so I think we can start by putting rest here for these. Right, notice I'm putting it in both because I know that if it's not going in a circle, that certainly means that there's no linear velocity either. At the same time, they told us that it's going to take 10 seconds, so whatever's going to happen takes 10 seconds to happen. Now, we were also given some information about a final speed. We're told it goes around once every 3 seconds. That sounds like an angular speed. Does it sound like that to you? Because it sounds like we got a rotation and a time. So I think that's an angular speed, 1 rotation every 3 seconds. Everybody good with that? And if you want, you can write this as 0.33 rotations per second. That's fine. That's all that was given, but you know there's problems coming up. But I'm not going to talk about the problems. I'm going to look at the fact that we can fill in every one of these blanks. Right? We could figure out how many rotations it took to get up to speed. We could look at how far the kid traveled while getting up to speed. We could look at what the angular acceleration of the ride was. We could also look at what the kid experienced as an acceleration. Because the angular acceleration of the ride is one thing, but the kid is sitting right here. They experienced something that made them feel like they were getting faster and faster. You guys know when you hit the, this is how we tend to make you feel like you're doing stuff without actually going anywhere. We just put you in a circle. That works. So we could figure out what that is. What was the tangential acceleration experienced by the kid? We could also figure out how fast is the kid actually traveling at full speed. These are all the things we could figure out. Let's figure out all of them. I'll point out that this side has our 3 pieces of information already. That means we could use those motion equations to work out this side. This side doesn't have those 3 pieces of information. But there's a bridge. There's something that bridges the angular side and the linear side. And that bridge looks like this. We know that if we're talking about displacement times radius equals linear displacement. That's the bridge. That's how we go from one side to the other. Well, I don't know either of those right now, so I can't bridge any of that information. But I also know omega times r equals v. Well, I have information there. I could use the bridge right now, right? I actually already did. I was going at 0 RPM at start, so it's 0 meters per second now. But I also know that at the end of the interval, I'll be going 1 rotation every 3 seconds. I could use that to figure out how fast I'm going there. Does that make sense? And of course, there's an angular acceleration because it started from rest and got up to some speed. That means the kid felt some linear acceleration. Like they hit the gas on the car and they start going faster and faster and faster. They would feel that in their back as they accelerate. So this is the bridge. So we have choices about the order in which we do things, but we're going to do all the same amount of work regardless. So I say we start by just filling in the angular side, right? Just shift this over and do the work for the angular information. So we're going to grab our, and we've done this already a couple times. This is what we practiced yesterday. So I think we can do this pretty quickly. And in fact, I'm thinking you don't need my help for this, right? Because we did this is our quiz yesterday, almost word for word. So take a minute, find delta, theta, and alpha, and I'll pick two of you, and hopefully you'll be right. All right, so we're doing okay so far? We are converting, we're using the bridge. Now, you have a choice. We have to find delta x. How far did the kid travel? There's more than one way to do it now. Do you notice that you have all of these? You could use a motion equation to figure out delta x if you'd like. You have delta theta, but you don't have it in radians. So you could convert it to radians and then use the bridge to figure it out. You have choices. Which one do you guys want to do? Do you want to use delta theta or do you want to use a motion equation? Use delta theta? All right, let's find this in radians first. It's rotation, so I just multiply by 6.28, and that will give me the value in radians. So 1.65 times 6.28, and I get 10.36 radians. All right, it's in radians now. I can use the bridge. So 10.36 radians times 2 meters equals 20.72 meters. Now, did the kid actually travel 20 meters away from where they were? No, they were traveling in a circle. The total distance traveled in 10 seconds was 20.7 meters, but they are probably right back where they started, or somewhere around that circle. They didn't go anywhere. They're not traveling in a straight line either. They're traveling in a circular path. But if we assume that this is the operating speed of the ride, this kid is traveling 4.2 meters per second now while they're on the operating speed of the ride. This acceleration was the tangential acceleration. They experienced this tangent to the circle, which means the acceleration they experienced was in this direction. This is the tangential acceleration. But, listen very closely, folks. The whole time, they were experiencing another acceleration because they were traveling in a circle. We can't forget the stuff we learned first semester. It's still a part of this semester. So the whole time they're traveling in a circle, they're also experiencing a centripetal acceleration this way. Something pushed on the kids towards the center of the circle. It started at 0 when they weren't moving and got bigger and bigger and bigger because the centripetal acceleration is based on how fast they're traveling and how big the circle is. So this is happening too. Now eventually, the kids make it to their top speed, right? Their top speed is 4.2 meters per second. When they make it to the top speed, if this ride is no longer speeding up, then at the top speed, this one goes away because they're not getting faster. They're not going to go any faster than 4.2 meters per second. Everybody understand that? That's the part where the ride's going and they're all going at the same speed and everybody's rah-rahing and hey, hey, ho, ho, having a good time. This one doesn't go away. This one stays because this is their centripetal acceleration. That's required to keep them traveling in a circular path. So for objects that are traveling in a circle, these are the tangential variables, as different than the centripetal one. I took too long, and so we're not going to be able to do our activity, and I feel bad. So we'll do the activity all day tomorrow. Sorry. Well, most of the day tomorrow. I don't think it'll take you that long. So if we finish a little early, we'll start on this other thing that I think you'll like. But tomorrow, so I'm using this one. We're going to try and figure out delta theta. And this is the information we were given. And I forgot to hit the record button, so I'm kind of reiterating it all right now in case somebody wants to watch this stupid video, because if all these people are not here today, they're never going to watch it anyway, so I don't even really care, but I'm doing it. So again, to work this out, figure out how many rotations the car tire makes as I come to rest, it looks like I travel 60 meters coming to rest. Does that make sense? Now there's one big difference in this problem. The car actually did go this distance, unlike the kid. The kid just went in a circle the whole time, but this is a rolling problem. So the car actually went this distance. Do you understand the difference in these two problems? So these aren't tangential velocities. The car was moving. It was going someplace. And it was the wheels that were rolling that helped the car get to that place. That's how it's different. So I'm not worried. I don't have to worry about centripetal acceleration and stuff like that. We're asked about the wheels, and I don't care about the wheels' centripetal acceleration. The whole car changed location. We're asking questions about the whole car. So this tells me how far the car went, but I would like to figure out delta theta. So the wheels have a radius of 0.4, so 60 meters equals delta theta times 0.4 meters. So I take my calculator, do some division, and I get that delta theta equals 150. Do you notice how the meters cancel out? It's going to come up on the test, and I want to make sure we understand this. The meters cancel out, but we know this is an angular measurement. If you have an angular measurement and there's no units expressed, it's got to be radians. Okay? So if the units cancel out, we're talking about radians. The reason that's important is when you're taking your next test, if you don't put the units next to it and you're supposed to give me something in rotations, even if the number is right, you could have meant radians. There's no way for me to know the difference. So you write radians or you write rotations. You make it clear. Everybody got it? There are 6.28 radians in every one rotation. So I need to convert this now to rotations. So you guys know how to do that at this point. So do I. So I get 24 rotations. That's how many rotations the tire made while we were stopping the car. All okay with this? All right, so I'm going to provide several examples of this with some answers. Maybe they'll be right this time. Don't expect it anytime, but I'm thinking Tuesday might ask you to try some of these, okay?